Great. So hi everyone, my name is Alex Lev, and I'll be discussing some joint work with Shen, Gabe, Jacob, and Vikash. So although language models are very impressive, their behavior is difficult to control reliably with prompts alone. And the starting point for our project was recognizing that many of the tasks we'd like language models to perform more reliably can actually be cast as posterior inference problems. So for example, consider the challenge of generating text subject to syntactic constraints. We might want to automatically translate a natural language query into a specialized DSL under the constraint that the output is well-formed code. Or we might want to rewrite a paragraph to be more accessible to people with reading disabilities like dyslexia by avoiding certain patterns that are difficult for them to parse. Or we might want to generate according to the constraints of a poetic form like a haiku. All of these can be viewed as posterior inference, where the prior is the language model's natural output distribution, and there's a 0-1 likelihood based on the syntactic constraint. Alternatively, consider the task of infilling, generating text that's not just based on a prefix, which these language models are sort of trained to do, but also a postfix, text that follows the text to be generated. So if in an IDE, we might want to auto-suggest completions based on the text both before and after the cursor. Right? Or if we have a data set of question-answer pairs, we might want to infer chains of thought that allow the language model to be better at answering the question, and then augment our training data with these synthetic chains of thought. We might want to figure out what prompt X could lead to some target behavior encoded by a postfix, and so on. All of these tasks are also posterior inference problems, where X is a latent variable and the prefix and the postfix are observed variables. As yet another example, we might want to generate responses that are likely to be classified as non-toxic or aligned with human preferences. This too is a posterior inference problem, conditioning on a stochastic classifier, F, identifying X as a member of the target class. So given all of these interesting posterior inference problems, it would be great to have some tools for defining and solving them. So in the rest of the talk, I'm going to tell you about a probabilistic programming library we've developed for this purpose, and say a bit about how we're approaching the challenge of efficient inference in this setting. So we're going to begin with a standard probabilistic programming library where programs can sample from primitive distributions and observe the outcomes of primitive samples. All of our distributions will be discrete, which means that there's a really simple way to understand the distribution that a program defines. Right? You can sort of imagine running the program. Anytime that you hit a sample statement, you just draw a sample from that distribution, and anytime you hit an observe statement, you sample from the distribution and check if you got the observed value. And if you did happen to get the observed value, you continue, and if you didn't, you reject and start all over, right? So this is a very inefficient inference algorithm, rejection sampling, but it's a good way of thinking of the semantics of a program that uses sample and observe if you haven't seen those before. And of course, the goal of an inference algorithm is to generate from the same distribution or an approximation to it, but much faster. So language model probabilistic programs are just probabilistic programs that use primitive distributions parameterized by language models. So in our library, users can create language model context objects with given prompts. And internally, these context objects are tracking the current prompt and the probabilities that a language model is assigning to the thousands of possible next tokens in the model's vocabulary. This distribution is exposed to users for use with sample and observe. And unlike most primitive distributions in probabilistic programming languages, these are stateful. When you either sample or observe a token, the context is automatically updated and a new next token distribution is computed. Now to get a feeling for how this works, let's look at an example. This is a task called Kali, put out by a group at Princeton last year, where the goal is to fill in each blank in this sentence with a word so that overall the sentence makes sense. It turns out that GPT-4 is quite bad at this. It tends to say things that aren't that fluent and that don't faithfully follow the template, like she gave her favorite book to calm down during the intense storm. And if you do some prompt engineering, you can get it to follow the template, but the sentences degrade even further in terms of their fluency. Like, after watching her mood started to down and she the cup gently. So let's see if we can write a probabilistic program to encode this task. It's pretty simple. We use a for loop to loop over the 13 words of the sentence, and we either sample or observe a word depending on whether the word is known or not. Right? One wrinkle here that's kind of interesting is that language models work with tokens and not words. So tokens can be subwords, so it might actually take multiple tokens in order to generate a full word. And it turns out that using sample and observe, you can actually write little helper functions that are probabilistic programs that help you express the idea of sampling a word or observing a word. And I'd love to talk about that more at our poster. So using LLaMA2 as the base model and a sequential Monte Carlo inference algorithm, we were able to get diverse and high-quality generations from the approximate posterior encoded by this program. Like, after a while, her dad had sat down to watch the midday news. Or throwing herself on her knees, she bent down to kiss the Holy Grail. But getting to inference to work well is non-trivial. So because language models work with sequences, it's often natural to apply a sequential Monte Carlo algorithm. The algorithm maintains a collection of weighted particles, each of which represents a possible generation. And at each step of inference, a resampling step decides how many descendants of each particle there will be based on their current weights. So higher weight particles will in expectation have more descendants. Then each child particle is created by extending its parent particle. So the illustration here is of a 5-particle run of a particular SMC algorithm for the model that we were just looking at. What I want to talk about is the various kinds of choices that go into making this model and making it work, and also what kinds of system improvements do we need over existing PPLs in order to make sequential Monte Carlo run fast in this setting. So in order to make things actually run efficiently in the system sense, we need 2 features that you wouldn't get for free just by integrating language models as primitives into Gen or Pyro or ProbTorch. First, it's really important to batch queries to language models wherever possible. If you have a GPU, it costs about the same to execute a single query as to execute dozens in parallel. And we really want to exploit that to enable high particle counts with minimal overhead. The typical way to support this in existing probabilistic programming languages would be to write your model in a vectorized way, so that the inference engine can run your model on a vector of particles. But this is really challenging to do for the models that we care about, where different particles are sampling different numbers of tokens and making different numbers of queries to the language model, and we use unbounded loops and other stochastic control flow. So instead of vectorizing, what our library does is it executes the SMC particles concurrently. And anytime the program requires a query to a large language model, that's represented as an asynchronous function call. So what that means in practice is that our implementation is going to switch between executing code for different particles until each particle is waiting on some language model query to resolve. Then we'll automatically batch all of those queries that are waiting, pad them out to the same lengths so that they can be executed efficiently on GPU, and then go back to the particles and say, here were your answers. So the sort of CPU logic is still executing sequentially, just or concurrently, but like on a single thread, whereas where it matters, we get the parallelism from a GPU. The second important feature is caching neural activations. So once the SMC algorithm has been running for a while, many of the particles share prefixes in common. And we've implemented facilities for caching the activations of those prefixes so they can be computed once and then used by all future descendants. So that's sort of optimizations for computational efficiency. What about improving the finite particle accuracy of inference? Well, there are 3 key degrees of freedom when designing an SMC algorithm that we can use as levers to improve accuracy. And we've designed our library to make it easy to experiment with all 3, because we sort of wanted to be able to iterate rapidly in this space and come up with design principles. So the first sort of lever that you have is what counts as a step, right? I have this big program, but how far am I extending things each time that I run a single sort of iteration of SMC? And when programs have stochastic control flow, it's really important that particles in different branches are paused at commensurate points for resampling, right? We want to make sure that when we pause to resample, it's fair to be comparing all of these different particles. The second degree of freedom is how to design the intermediate target distributions. That is, how to tell whether an incomplete particle is on the right track. And the third is the proposal distribution. How should the algorithm propose an extension of the parent particle? And you can actually vary all of these freely, and you just have to update the way that you're computing the weights, and it's still a valid SMC algorithm that's targeting the same distribution that your program denotes. Now, what's actually, I think, really, we've been exploring a lot of strategies for this, and I'd love to talk more at the poster. I'm bolding a few, because what's really interesting about the language modeling setting is that you can kind of use a language model to parameterize all of these choices too. We can use language models as proposal distributions. We can tell them, hey, this is the inference task that you're trying to solve, and they can output proposals. We can use the language models as what are called twist functions, basically ways of twisting the intermediate target distributions based on some prediction about whether the particle is on the right track. We can also even use language models to decide when to stop a step, right? We can ask the language model to output a particular token for, hey, I've sampled a semantic unit. Please stop me now and compare me to the other particles that are at a similar place. We have some preliminary results in some different domains. There are more on our poster, and I would love to chat. One that's really fun is this reversible phrase generation example that comes from this Sparks of AGI paper that Microsoft put out last year. They noted that GPT-4 was really bad at things that required planning, like, please generate a first line of a poem that could plausibly be reversed to form the ending line of a poem. So it comes up with things like dawn silence whispers softly, evenings echo fades, but if you try to read that backward, fades echo, evening softly whispers, silence dawns, it doesn't really make much sense. We can encode this as a probabilistic program, and we get things like, cold and dark was it when winter last winter when it was dark and cold. Or, are we there yet? Yeah, there we are. There was nothing but love in her eyes her in love, but nothing was there. Another reason that I'm excited about this work is it's just really fun to write probabilistic programs and play with them in this framework. So I'm also excited about the sort of pedagogical implications of having a library like this available in teaching ideas for modeling and inference. Cool, thanks.